Hey everyone, welcome back to our production-focused LLM series. Today we're covering the complete guide to inference caching, a powerful technique that dramatically cuts costs and latency when running large language models at scale. If you're building real-world applications that call LLMAPs frequently, mastering inference caching can save you serious money while delivering much faster responses. Let's break it down clearly from the fundamentals all the way to practical implementation strategies. Calling LLMAPs at scale gets expensive fast because the same system prompts and common queries cause repeated heavy computation every single time. Inference caching solves this by storing expensive computations at different levels and reusing them for identical or similar requests. You can apply it at 3 complementary layers to skip redundant work inside a request, reuse shared prefixes across requests, or serve similar queries without calling the model. In production, this can significantly reduce token spend with almost no changes to your existing application logic. Now let's start with the fundamentals of inference caching and why it matters so much today. When you send a prompt to an LLM, the model performs heavy computation to process the input and generate each output token one by one. Caching stores those computation results at different granularities so similar requests can reuse the work instead of starting over. There are 3 main types of inference caching, each operating at a different layer of the stack. First is KV caching, which stores the internal key-value pairs from the attention mechanism inside a single inference request. This mechanism runs automatically in every modern LLM framework and stays enabled by default. To understand why KV caching is powerful, let's look at how transformer attention actually works during generation. For every token, the model computes 3 vectors: query for what it needs, key for what the token offers, and value for the information it carries. Attention scores compare each query against all previous keys, then weight the values to understand full context. LLMs generate text autoregressively, producing 1 token at a time. Without KV caching, generating each new token requires recomputing keys and values for the entire previous sequence from scratch. With KV caching, the stored key and value pairs for past tokens are simply loaded, so only the newest token needs fresh computation. This eliminates redundant attention work during the decode phase and forms the foundation for all other caching techniques. Now that we understand KV caching inside one request, let's explore prefix caching, which extends it across multiple requests. Prefix caching reuses the KV states for any identical leading tokens, such as a long system prompt, reference documents, or few-shot examples. In most applications, the system prompt stays exactly the same, while only the user message changes each time. Without prefix caching, the entire shared prefix gets recomputed on every single request, wasting valuable compute. With prefix caching, the shared part is processed only once, stored, and every matching request jumps straight to the new content. The strict requirement is a byte-for-byte exact prefix match. Even 1 character difference invalidates the entire cache. That's why you should structure prompts with all static content first and dynamic user content last. Also, avoid non-deterministic formatting, such as varying JSON key order, which breaks exact matching. Major providers make prefix caching straightforward to use in production. Anthropic offers prompt caching by adding a cache_control parameter to specific content blocks you want cached. OpenAI applies prefix caching automatically for any prompt longer than 1024 tokens, using the same leading prefix rule. Google Gemini provides context caching, and charges separately for stored cache, ideal for very large, stable contexts. Open-source engines like LLM and SGLang handle automatic prefix caching transparently, with no extra application code needed. With that foundation in place, let's move to semantic caching, which operates at the full application level. Semantic caching stores complete input-output pairs and retrieves them based on semantic similarity using embeddings rather than exact tokens. For a new query, you compute its embedding, then search a vector store for high cosine similarity matches above your chosen threshold. If a strong enough match is found, you return the cached response instantly, without calling the LLM at all. If no good match exists, you call the model normally, store the new pair with a time to live, and return the result. Popular production vector databases for semantic caching include Pinecone, Weaviate, or pgvector. Semantic caching excels in high-volume FAQ applications, customer support bots, or anywhere users frequently paraphrase the same questions. Remember, these three types are complementary layers that work best when combined intelligently, rather than used as replacements. KV caching always runs automatically with nothing extra to configure. Prefix caching usually delivers the biggest wins for most applications by handling shared system prompts or RAG documents. Semantic caching adds extra value on top when you have high query volume and strong similarity patterns. Here's a clear decision framework to help you choose the right strategy for your own use case. All applications should always use KV caching, since it runs automatically and is always on. Apply prefix caching when you have long shared system prompts or stable RAG reference documents. Agent workflows that maintain large, stable context also benefit strongly from prefix caching. For high-volume applications where users often paraphrase the same questions, layer semantic caching on top. What caching strategy are you planning to try first in your own projects? Drop your thoughts and implementation plans in the comments below. Please hit the like button right now, subscribe, and turn on the bell icon so you never miss future deep dive tutorials on production LLM techniques. See you in the next video. Stay optimized and keep building.